Everything you see, stars, planets, even you, will end someday. Scientists have narrowed the possibilities to a few strange finales: a slow, heat death, where the universe winds down and cools like a forgotten cup of coffee, a big rip that stretches space until things tear apart like taffy, or a big crunch that collapses everything back like a squeezed balloon. In the next few minutes, first we'll explain those endings in plain language, show the simple observations that point us toward one outcome, and tell you what each scenario would actually mean for life and the future. No PhD or scary equations required. You'll walk away knowing the real odds, a couple of surprising twists, and why the cosmic finale is more curious than catastrophic. Spoiler, it's less Hollywood explosion, more very slow, very weird fade out. The long, slow fade, heat death. Entropy tends to increase, and that simple rule is the heart of this particular cosmic ending. Over time, energy spreads out until it can no longer do useful work. Entropy is just a way of measuring how mixed up or how evenly spread energy has become. Think of it as the universe getting more stirred. Pour cream into coffee and watch it swirl until the colors are one. You cannot unmix them without putting in extra work. Short sentence. This everyday example mirrors the basic idea. Once everything is spread evenly, engines stop running and stars stop shining. Stars shine because they use concentrated fuel and squeeze it until fusion releases lots of energy. When that fuel is gone, the star cools and becomes a faint remnant, like a battery that's been drained and left on a shelf. Some remnants are dense and quiet, such as white dwarfs and neutron stars, and some are extreme enough to form black holes. Black holes are weird objects that concentrate mass and energy, but even they are thought to slowly leak energy through a quantum process called Hawking radiation, meaning nothing is eternally immune to the gradual fade. A short life, a longer afterlife. Funny, but not theatrical. Space itself is stretching, which pulls light and other energy apart so they carry less punch as they travel. Photons lose energy when wavelengths stretch. This is called redshift, so the background glow of the universe grows dimmer and cooler over time. If everything ends up at the same low temperature, there are no heat differences left. No heat differences means no engines, biological or mechanical, can extract work. Imagine trying to run a car when both the engine and the surroundings are the same chilly temperature. It won't start. The subtle point is that life and machines all need gradients, hot versus cold, high versus low, to do anything useful. Structures like galaxies and solar systems depend on matter being clumpy enough to pull together and form new stars. If matter is too thinly spread, new stars can't form and old ones die out, leaving a dim, thinly populated cosmos. Picture a party where friends slowly drift to different rooms and the music fades until everyone is in separate corners. Conversation becomes impossible. Small, local pockets of activity might linger for an extraordinarily long time, but they become rarer and more isolated, like tiny candles in a vast, silent hall. The overall picture is not an explosion but a gentle fading. Light grows faint, motion slows, and the universe moves toward thermal sameness. It's a bleak and peaceful outcome, more long nap than dramatic finale. Still, there is a kind of strange beauty in the idea that the laws we use every day, the ones that make your refrigerator and your car work, also predict this very slow, inevitable quieting. On the bright side, the universe won't go out with a bang, it will just dim the lights and politely leave the room. When gravity wins, the big crunch. If the stretching of space that carries galaxies apart were to slow and stop, gravity could take over and start pulling everything back together. Space itself would stop growing and then shrink, bringing galaxies, stars, and gas closer until their motions were dominated by mutual attraction. You can picture this as the reverse of a balloon inflating. Instead of dots moving away as the surface stretches, the surface would compress and the dots would converge. That simple shift in who's in charge, expansion or gravity, changes the whole story. Galaxies that once drifted apart would begin to meet. Collisions would be common. Stars would slam into one another or be thrown out of their homes by gravitational tugs. Entire galaxies would merge and ripple like cars piling into a massive, slow-motion traffic jam. As material concentrates, the energy tied up in motion and compression turns into heat and light, so regions that were once cold and sparse would grow blisteringly hot. Life as we know it relies on delicate conditions. Those conditions would vanish long before the final collapse. As matter keeps compressing, black holes could merge into ever larger objects, swallowing up stars and gas. Eventually everything might be concentrated into an enormously dense state, so dense that our current theories stop giving clear answers. Think of squeezing a sandcastle until it's a single lump, only the forces involved here are far more extreme and stranger than anything on a beach. The end game could be a single, ultra-compact region where space, time, and the familiar rules blur and require new physics to understand. This scenario is hypothetical, but it helps to use everyday examples to get the idea across: a crowded elevator feeling increasingly tight, a loaf of bread collapsing so the raisins come together, or a traffic jam where the pile-up grows until nothing moves. It's a dramatic, everything back together outcome driven solely by gravity winning the contest. Whether the universe will follow this path is still an open question, but the big crunch picture shows clearly how the same pull that makes apples fall could, in principle, reverse the universe's expansion and bring a very large cosmos to a very small ending. Tearing apart, the Big Rip. The universe is getting bigger and that growth is speeding up, driven by a mysterious push that acts like anti-gravity. If that push not only continues but grows stronger with time, it could overcome every force that normally holds things together, from the gravity keeping galaxies intact down to the chemical bonds that hold atoms together. Picture something that starts by gently stretching a blanket and ends by pulling the threads apart one by one. It's a radical possibility, but scientists use it to test how well we understand the push that makes space expand. Normally, expansion affects the space between things that are already far apart, while nearby objects stay bound by their own glue: gravity for stars and planets, electrical forces for atoms. In the stronger push scenario, that glue fails in a predictable order. The biggest, loosely held structures drift apart first, and then progressively tighter systems come unstuck. Galaxies that used to travel together would separate, solar systems could lose planets from their orbits, moons might drift off. Finally, if the push kept increasing, molecules and atoms could be pulled apart. Think of it like stretching a piece of taffy: first the big blobs pull away, then the candy thins, and eventually the sugar threads snap. Astronomers look for signs of this by measuring how fast cosmic expansion changes, using exploding stars as distance markers and surveys that map galaxy positions and motions. Current measurements show the expansion is accelerating, but to make the extreme tearing scenario happen you need a particular kind of energy that gets stronger over time. That specific behavior is not demanded by current observations, it's one possibility among several. So while telescopes have given us clear evidence of acceleration, they haven't shown the relentless, ever-growing squeeze that would guarantee a cosmic shredding. For life and everyday things, the implications are dramatic in theory. If the tearing power reached the scale of planets and atoms, no sheltering, or running would help. Bonds that keep matter together would fail, and even tiny particles would be affected. It's fair to say there would be no need to pack a suitcase. On the bright side, this is a speculative outcome contingent on a very particular behavior of the mysterious push. Much of modern astronomy is devoted to testing whether that behavior is real. Until then, the picture remains a thought-provoking blend of real measurements, careful math, and a little cosmic drama that's best enjoyed from the safety of current observations and a sense of humor. Quantum betrayal, vacuum metastability and false vacuum decay. Our vacuum, the background state of space that gives particles their everyday behavior, might not be the deepest, most stable arrangement possible. Think of the vacuum like a ball sitting in a shallow dip on a tabletop. It looks comfortable and unmoving, but a deeper hole lies beyond a small ridge. In quantum physics, that ball can sometimes pop through the ridge without climbing it, a process called tunneling, and land in the deeper hole. This is what scientists mean by a metastable vacuum. It seems stable, but quantum effects can cause a sudden switch to a more stable state. A tiny region can flip to that deeper state and create a bubble that grows outward. The wall of the bubble is a moving front where the rules of physics change, and it races through space at nearly the speed of light. Short sentence. Anything the bubble hits would be rewired, atoms, chemistry, and even the forces holding matter together could be altered or destroyed. You would not see it coming, no alarm bell could travel faster than light to warn you, so by the time information reaches you the wall would already be on top of you. Why should anyone care about fields and dips in an abstract plot? Because the Higgs field, the thing that helps give particles mass, might be precarious in this way. Measurements of the Higgs and the top quark leave open the possibility that our vacuum is only metastable. That does not mean doom is imminent. Most interpretations of current data suggest that if a decay can happen, it would be staggeringly unlikely on human timescales. Still, scientists continue to tighten those measurements using particle experiments and cosmological observations, like checking the seams on a garment to see if the stitch will hold. No practical defense exists against a bubble of true vacuum. Building a bunker, launching a signal, or negotiating with the universe will not help. Short and uncomfortably final. The only realistic response is better knowledge, more precise experiments narrow the odds, and better theory explains how the potential landscape of fields is shaped. For a human-scale analogy, it's like noticing a hairline crack in a dam. You can study it carefully and learn whether it will slowly grow or never matter, but you cannot stop the sudden collapse if quantum chance decides otherwise. A bit grim, perhaps, but at least the possibility motivates clever physics and a wry appreciation for how strange the cosmos can be. Proton decay and the dissolving matter. Protons are tiny, positively charged parts at the center of atoms, and every solid thing around you is built from atoms stacked together. In everyday life they behave as if they will last forever. Every experiment done so far has found protons to be incredibly stable. Some theories in physics, though, suggest that protons might not be truly immortal but could slowly change into lighter particles in a process called decay. That idea comes from attempts to unify different forces into a single picture, and it would mean that the very bricks of matter can, in principle, disappear. Experiments buried deep underground with big pools of water and sensitive light detectors have been watching for the faint signs of a proton flipping into other particles. None of those experiments have seen a clear decay yet, which tells us that if protons do decay, it happens so rarely that each one can sit peacefully for times far longer than the life of stars we can see. Think of it like a raffle ticket that almost never wins. Most tickets exist for a ridiculously long time before one is called. Because the chance per proton is so tiny, there is no practical effect on human timescales or on any technology we use today. If proton decay does turn out to be real, the long-term consequences for the universe are simple and dramatic. Ordinary matter would slowly dissolve. Atoms are held together by nuclei made of protons and neutrons. Take away protons and the nuclei fall apart. When a nucleus disintegrates, electrons that once orbited it would be left wandering, and the chemical bonds that make solids, liquids, and gases would break. Imagine a sandcastle built from grains that very slowly, one by one, vanish from inside the walls. The castle would not collapse in a sudden wave but would thin and crumble over unimaginably long stretches of time. To picture the process, picture a massive bank account where a single penny disappears now and then from a different account every trillionth of a second. For any single object, the chance that it loses a particle in your lifetime is effectively zero. But given enough time and enough protons, every atom will eventually be affected. Those wandering electrons and decay products would produce light and other particles, so matter would slowly wash away into radiation and simpler bits. Chemistry would end. Complex structures like planets, rocks, and biological molecules would not survive indefinitely. It's a slow fade-out rather than an explosion. There's a slightly funny image that helps, a Lego house whose bricks occasionally teleport away. First you don't notice. Then a doorway springs a leak. Eventually the roof sags. In the cosmic version the teleportation is unimaginably rare per brick, and the house is the size of a planet. The key point is that dissolving matter from proton decay, if it happens, is not a nearby threat or a sudden catastrophe. it's a theoretical endpoint mechanism that acts on scales so vast that human concerns remain unchanged. Scientists keep searching because the answer matters for how we understand the laws of nature. Finding proton decay would be like discovering a hidden rule book for the universe and would explain why matter behaves the way it does on the deepest level. Not finding it keeps other ideas alive. Either way, the concept helps explain one possible way the universe could end, not with a bang everyone feels, but with the slow, patient disappearance of the very stuff that makes up everything we know. Black hole evaporation, the universe's tiny flares. Black holes are not truly eternal objects, they slowly lose mass by giving off faint radiation that escapes into space. This happens because the rules of tiny particles, what physicists call quantum effects, allow pairs of particles and antiparticles to flicker into being near the black hole's edge, and sometimes one member of the pair falls in while the other manages to slip away. The escaped partner shows up as real radiation, and the hole's mass goes down a bit to pay the energy bill. That predicted leak is usually called Hawking radiation, a simple way to name a quantum glow from something you thought swallowed all light. Smaller black holes radiate more strongly than larger ones, which sounds backward until you think of an everyday comparison. A tiny ice cube melts faster in your drink than a hulking block of ice would. In the same spirit, a small black hole is hotter and shrinks faster. A giant one is extremely cold and hardly changes at all on human timescales. For typical black holes born from collapsing stars, the emission is so weak that it's effectively invisible to us. It's like expecting a campfire from a single cigarette ember. Physicists have even built lab systems that imitate aspects of this effect, using fluids, light, or ultra-cold atoms, to study the idea in controlled conditions, because the real thing is too faint to catch directly with our telescopes. As a black hole loses mass, its temperature rises, and the process accelerates, making the final act potentially dramatic, a rapid release of high-energy particles and light, a tiny flare at the end of a very long life. The details of that finale are uncertain, though, because we step into the messy intersection of gravity and quantum mechanics where current theories get fuzzy. Think of it like watching embers in a fireplace. Most of the night they glow faintly, then very briefly one pops and sends a tiny spark, only here the pop is governed by physics we don't fully understand yet. Observationally, this slow evaporation doesn't affect our daily life, but it matters a lot for understanding fundamental physics and the ultimate fate of matter in the universe. The idea also gives a clear target for experiments and theory: detect extremely faint radiation, improve analog laboratory tests, and reconcile what happens in the last moments with a complete quantum theory of gravity. In other words, it's both a tiny curiosity and a big clue, like finding a single loose thread that might unravel a whole sweater of cosmic mysteries. Plus it's amusing to think of the universe ending in a series of tiny, stubborn flares rather than a grand fireworks finale. Stellar farewells, how stars die out. Stars shine by steadily turning light elements into heavier ones at their centers, a process that releases enormous amounts of energy and holds the star up against gravity. This central engine is like a long-running stove. As long as there is fuel and heat, the flame keeps the pot from collapsing. When that fuel changes or runs low, pressure drops and the star responds, often in dramatic fashion. Smaller stars, roughly the size of our sun or less, run out of their most easily burned fuel and start to swell. Their outer layers puff outward and cool, giving the star a redder, bloated appearance. Think of a balloon getting warmer and expanding. Those outer layers can drift away, creating a glowing shell of gas that looks delicate and ornate in telescopes. Astronomers call these shells planetary nebulae, but they are nothing to do with planets. A better everyday image is a soap bubble lit from inside. What remains at the center is a white dwarf, which is effectively a dense, hot ember no longer making new fuel. It's roughly as compact as a planet like Earth but carries most of the star's original mass, and over time it cools and fades, much like a coal dying down in a fireplace. Massive stars take a different route and go out with a bang. Their cores make heavier and heavier elements until the central pressure can't hold up against gravity, and the core collapses suddenly. The collapse rebounds in a titanic explosion called a supernova, which can briefly outshine an entire galaxy and scatter the star's material far and wide. From that wreckage can come exotic leftovers, a neutron star, which is unimaginably dense and behaves like a giant atomic nucleus packed into a city-sized sphere, or a black hole, whose gravity is so fierce that not even light escapes. To borrow a household image, it's like a pressure cooker whose lid blows off, except the pressure cooker becomes part of the kitchen floor. Binary star systems add more twists. If a compact remnant such as a white dwarf steals matter from a nearby companion, it can be pushed over a limit and explode in a thermonuclear blast, sometimes wiping itself out in one spectacular show. Two white dwarfs merging can do the same thing. This stellar thievery and merging are more common than you might expect and often produce fireworks that serve as signposts for astronomers. Picture a cosmic ballroom dance where partners get too close and one of them loses their shoes, messy, dramatic, and memorable. One important practical outcome of these deaths is that stars seed the surrounding space with the elements life needs: carbon, oxygen, iron and more. Those elements join clouds of gas that may later collapse into new stars, planets, and ultimately the raw materials for life, so every star's ending helps set the table for the next generation. It's like composting on a cosmic scale, the messy remains of one life feed the next. Stars therefore die in many ways, quietly, flamboyantly, slowly, or explosively, but nearly all of those endings are acts of recycling that keep the universe lively, and that, when you think about it, is a cheerful kind of farewell. Galaxy isolation, islands in an expanding sea. Many galaxies will one day slip so far from us that their light can never catch up, and that simple fact shapes the lonely future of the cosmos. The reason is that space itself is stretching, and whatever is causing that, usually called dark energy, acts like a steady push that makes distant objects speed away faster over time. A useful way to think about the limit this creates is the cosmic horizon, a moving boundary beyond which events cannot send information or light to us anymore, because the space between grows too quickly. This is not imagination. Astronomers use observations of galaxy motion and light to infer that the universe's expansion affects what we can see and what we cannot. Within our local neighborhood, gravity still wins small battles. The Milky Way and nearby companions such as Andromeda are part of the local group, a collection of galaxies bound together by their mutual pull. That means they will remain close, orbit one another, and eventually merge into a single larger system, rather than being carried away with the expanding sea of space. Think of it like houses on the same island that stay connected by footpaths, while boats pull away from the island's shores. The local cluster becomes an island of stars in a widening ocean. As other islands drift beyond the horizon, the night sky will grow emptier in a very particular way. Light from faraway galaxies gets stretched to longer, redder wavelengths as space expands, a process called redshift, and eventually that light shifts out of the visible range and fades. It is a bit like turning the dial on an old radio. Distant stations become static and then go silent. Future observers living in our island galaxy would see far fewer external galaxies, and the ones left would be the members of their own gravitational neighborhood. The practical effects for measurement and discovery are profound. Evidence of the wider cosmos becomes harder to collect when the sources are gone or too faint. Cosmic background glow and the pattern of distant galaxies, which today help scientists infer the universe's history, become progressively obscured. That leaves local clues, motions of nearby stars and the composition of gas and stars in the island galaxy itself, as the primary record. It's like trying to write the history of a nation using only family albums. You can learn a lot, but certain chapters will be missing. Everyday examples help make the picture less abstract. Picture a coastal town where ferries used to connect to many places. If the sea rises and currents strengthen, the ferries stop reaching distant ports and the town becomes effectively cut off. Or think of a neighborhood where only the houses on the same block stay in touch by walking over, the rest are reachable only by a plane that no longer flies. A touch of humor helps. It's the cosmic equivalent of getting stranded on an island and discovering your Wi-Fi only works for your neighbors. Despite the loneliness, life on such an island is not empty. Stars will continue to be born from the gas that remains, collisions and mergers will sculpt a large local galaxy, and complex structures can still arise within the island's bounds. The universe becomes a landscape of isolated archipelagos, each with its own history and future, and studying one of them still offers rich and meaningful science. The long-run image is sobering but also oddly intimate, a universe where each remaining gravitationally bound group of stars becomes a closed, thriving neighborhood set against an ever-receding horizon. Dark energy, the mysterious driver of destiny. Observations show the expansion of space is speeding up, and the cause we call dark energy makes up roughly 70% of the universe's energy content. This is not a stray guess, it comes from measuring how far away galaxies and exploding stars appear and from mapping the patterns of matter across the sky. In plain terms, dark energy behaves like a smooth, invisible substance that fills space and gently pushes things apart, rather than pulling them together the way gravity does. Think of the universe like a loaf of rising bread with raisins stuck in the dough. As the dough rises, the raisins move away from each other because the space between them grows. Dark energy is what makes that dough rise faster and faster. It's not that galaxies are racing through space like cars on a highway, space itself is stretching, carrying the galaxies along like confetti on a river. A balloon with dots drawn on it is another simple example. As you blow it up, the dots move away from one another, and if the balloon's stretching speed increased, the dots would separate ever more quickly. Scientists don't yet have a direct detection of dark energy, they infer it from several consistent lines of evidence. One strong clue came from bright explosions known as supernovae, which act as cosmic lighthouses to measure distance. Surveys of how galaxies cluster and faint patterns in the leftover glow from the early universe add matching evidence. Telescopes today continue to map millions of galaxies and watch those supernovae, because the more precise the map, the better we can tell whether dark energy is a steady push or something that changes with time. It's a bit like using many clocks and speedometers to figure out whether a car is coasting, accelerating, or being pushed by a mysterious gust. There are a few leading ideas about what dark energy actually is, explained in simple language. The simplest is a uniform energy that fills space and never changes, like a broth that tastes the same no matter how large the pot. Scientists call that the cosmological constant, but the idea is easy: each cubic meter of space has a tiny, steady push built into it. A second idea imagines a field that can vary, a moody energy that changes slowly over time, sometimes pushing harder or softer. That option is often called quintessence. Think of it as a thermostat slowly drifting up or down. A third route says maybe our understanding of gravity itself needs tweaking, so the rules that tell masses how to pull on one another are different on the largest scales. In everyday terms, it's like discovering the map you've been using has a different scale once you cross into a remote region. The nature of dark energy determines the long-term outcome of cosmic life. If the push is steady and gentle, galaxies outside our local neighborhood will speed away until they're forever out of reach, star formation will slow, and the universe will become darker and colder over unimaginable stretches of time. If the push grows stronger, more dramatic outcomes are possible, up to a scenario where structures are torn apart, though that is more speculative. Locally bound systems, like galaxies and solar systems, are safe from the accelerating expansion for now. Gravity wins on those scales, at least for the time being. So no sudden cosmic shrug at breakfast. Work continues in labs and observatories because pinning down dark energy is one of the clearest ways to learn if a new physical principle is hiding in plain sight. Better maps, more supernovae, and precise measurements of how galaxies drift will narrow the options. For everyday life, this research is mostly philosophical and inspirational. It reshapes a deep story about the cosmos rather than changing how you charge your phone. Still, understanding a force that governs the fate of the universe is a high-stakes kind of curiosity, and pursuing it often drives innovations in detectors, computing, and data analysis that do ripple back into practical tools. A little mystery and a bit of humor help. The universe might be heading for an uncertain future, but at least it keeps scientists busy and comedians supplied with material. Entropy and the arrow of time. Every isolated system tends to move toward states that can be made in more ways, which is the practical heart of what people call entropy. Put simply, entropy is a count of how many microscopic arrangements can give the same visible outcome. If there are lots of hidden arrangements, entropy is high. For example, a tidy bookshelf has low entropy because there are only a few ways to place each book and keep it looking neat, whereas a pile of books on the floor has high entropy because there are many more possible jumbles that look like a messy pile. That difference in possible arrangements drives why things naturally go from neat to messy more often than the reverse. The rule that entropy tends to increase in a closed system is not a magic law imposed on particles, it's a statistical fact about large numbers of things. When trillions of atoms are involved, the number of ways to be disordered vastly outnumbers the ways to be ordered, so disorder is simply much more likely. Think of shuffling a deck of cards. A well-ordered deck can be recreated, but the chance that a single random shuffle will restore perfect order is astronomically tiny. Short sentence for emphasis. That's why spilled milk spreads out across the counter and doesn't jump back into the glass. Microscopic laws of physics themselves mostly don't care about time's direction. At the level of a single atom or a billiard ball, the equations work forwards and backwards. But when huge numbers of particles act together, statistical behavior emerges and an arrow appears, pointing from past states of lower entropy to future states of higher entropy. This is why memories and cause and effect feel one way. Writing a note increases entropy as ink spreads and paper fibers rearrange, and forming that memory relies on physical changes that are highly unlikely to spontaneously reverse. Everyday appliances highlight the trade-offs. A refrigerator keeps its contents cold and locally decreases entropy inside the compartment. However, it expels more heat to the room and uses electrical work, so the total entropy of the room plus fridge increases. Short, clear point. The same goes for cleaning a room. Effort and energy are required to reduce local mess, and that effort produces waste heat and other increases in entropy elsewhere. Entropy also connects to information in a practical way. When a system has low entropy, you need to know more specifics to describe it accurately. High entropy means many specific details don't matter because they average out. Consider a photograph of a crowded beach. You can describe a busy beach with few details and still be correct, but to recreate the exact moment you'd need a lot of precise information about each person's position. In computing, erasing a bit of information must be accompanied by some energy cost and heat release, so information processing is tied to thermodynamic bookkeeping. People like to joke that the reason toast falls butter side down is entropy, and there's a grain of truth in that kind of humor. The exact outcome of that minor tumble depends on many small influences: angles, air currents, the way the table and toast interact, and the messy, more probable outcome tends to win. Short and slightly comic. A broken vase doesn't reassemble because the many shattered particles have settled into a state with far more microscopic arrangements than the neat vase ever had. Finally, the arrow of time that comes from entropy shapes large-scale futures as well as small daily events. Processes that mix, spread out, or dissipate energy tend not to reverse, so long-term behavior heads toward states where energy differences are smoothed out. Practical takeaway: to keep things organized or to maintain gradients, like a hot engine or a cold freezer, we must constantly spend energy. Entropy is the bill that keeps coming. A little grin helps here. Nature is polite but persistent about collecting its dues. Observing the end. What astronomers can measure. Astronomers measure the universe's expansion by looking at how the light from galaxies is stretched toward redder wavelengths, a phenomenon called redshift. This is the same effect that makes the pitch of a passing ambulance change, but with light instead of sound. When a galaxy moves away, the light's waves broaden and shift. Distances are measured using standard candles, such as certain exploding stars whose true brightness we can estimate, so by comparing observed brightness to intrinsic brightness we get how far away they are. Telescopes on the ground and in space collect spectra and brightnesses for thousands of objects, and combining those measurements traces how the expansion speed changes with distance, a direct clue to whether the cosmos will keep speeding up or slow down. The faint glow left from the Big Bang, known as the cosmic microwave background, gives another kind of measurement: its temperature and tiny variations across the sky. Think of it like the last embers of a fire that cooled and spread, carrying tiny cool and warm spots that tell a story about the early mix of stuff. Sensitive detectors map those little bumps and dips, and from their patterns scientists infer the overall makeup of the universe, how much ordinary matter, dark matter, and the mysterious dark energy there is, and whether space is curved like a saddle, a sphere, or flat like a tabletop. Satellites and high-altitude instruments do this work, and the patterns they find act as a baseline against which future changes are measured. The way galaxies clump together and how those clumps grow over time is another key observable. Surveys that map millions of galaxies reveal a cosmic web of filaments and voids. By measuring how those structures evolve, we learn how gravity and the accelerating push of dark energy compete. Gravitational lensing offers a clever trick. Mass bends light, so distorted shapes of background galaxies let astronomers map invisible mass directly, like using a funhouse mirror to know what's hidden behind a curtain. Gravitational waves, ripples in spacetime from colliding black holes or neutron stars, add complementary data by revealing the behavior of gravity in extreme places, and they can act as independent distance markers when paired with light. Local clocks in the sky also matter: ages of the oldest stars, rates at which new stars form, and the growth history of supermassive black holes provide timekeeping for cosmic evolution. Chemical fingerprints in starlight tell whether successive generations of stars enriched galaxies, and that history constrains models of how structure will evolve in the long run. Measurements of cosmic neutrinos and attempts to detect relic neutrino backgrounds are ongoing. Even if those are faint and elusive, each improved limit narrows possible endings. In short, collecting many different kinds of precise observations is like improving a weather forecast for the far future of the universe. Better data shrinks the range of plausible outcomes, and that is the practical goal of what astronomers measure. Cosmic collisions and accidental catastrophes. Our planet shares space with countless chunks of rock and ice that sometimes cross its path, and most of these are harmless because they are tiny and burn up in the sky. A small rock entering the atmosphere becomes a bright streak called a meteor, and if any piece survives to hit the ground, it's a meteorite, like a tiny space pebble showing up at your front yard party. Big pieces are much rarer, but a large impact can throw dust into the air, cool the surface, and disrupt food chains. Think of the way a campfire's smoke can make it hard to breathe and see for everyone nearby. The giant gas planets in our system act like big vacuum cleaners or bumper cars, tugging and catching some of these objects so fewer head inward toward Earth. Collisions aren't limited to rocks hitting planets. Whole space systems crash into each other on slow, cosmic timescales, and even close encounters can change orbits. When two objects pass near each other, gravity can act like a tractor beam, pulling one into a new path. Sometimes that gentle nudge sends something straight toward us. This is similar to how one car merging into traffic can force another to swerve. Consequences can be small or catastrophic. Stars and black holes can merge too, releasing enormous energy that we detect as ripples in space, but those distant fireworks rarely pose a direct threat to life on Earth. Human activity has added a new kind of collision risk: the clutter in near-Earth orbit. Satellites and discarded rocket parts can collide, creating fragments that travel at very high speeds. That scenario is known as the Kessler syndrome, where one breakup leads to many more, like a chain reaction of falling dishes in a crowded kitchen. Space agencies already track thousands of pieces, and collisions have occurred, producing clouds of debris that make future launches riskier and can interrupt services we take for granted, such as GPS, weather monitoring, and communications. Accidents caused by attempts to fix or move cosmic hazards are another concern. Trying to break a threatening asteroid into pieces could accidentally turn one big danger into many smaller dangers, each on its own unpredictable path. It's the space version of shaking a beehive to get rid of a single bee and scattering a whole swarm. Even well-intentioned tests of deflection need careful planning, because hitting a target at high speed can shatter it, spread fragments, and complicate rescue efforts. The lesson from everyday life applies: sometimes a gentle push is better than a smash, and planning matters. Prevention focuses on watching and planning, not hoping nothing happens. Telescopes and radar keep track of near-Earth objects, and humans are developing methods to gently change an object's course, rather than blowing it apart. For orbital debris, ideas include designing satellites that burn up cleanly, removing junk with nets or tugs, and coordinating launches so traffic on the orbital highway flows smoothly. Those are practical steps, and they work a lot like clearing a congested freeway. Better coordination and a few good tools reduce the chance of a pileup. A little patience, careful engineering, and international cooperation go a long way toward turning potential cosmic disasters into manageable problems. Cyclic and bouncing universe models. Some cosmologists propose the universe goes through repeated phases of growing and shrinking, rather than having just a single beginning and end. In these ideas, a contracting phase follows an expanding one, and instead of hitting a hard, infinite density wall, the universe bounces back into expansion. Think of it like a cosmic trampoline. The universe falls, the physics of extreme density gives a push, and then it rebounds. This avoids the idea of a mathematical breakdown where our usual laws stop working, though the details of the rebound require new physics that we don't yet fully understand. Different mechanisms have been suggested to make the bounce happen without turning everything into a science fiction soup. One approach imagines that space itself becomes a bit grainy at the smallest scales, that microscopic structure acts like a repulsive force when density gets very high, stopping the collapse and initiating expansion. Another picture comes from higher dimensional theories where our universe is like a thin sheet, and a collision with a neighboring sheet can look to us like a big crunch followed by a new bang. Both ideas replace the singular, everything in one point scenario with processes that can be described, at least in principle. A helpful life example is a compressed spring. Push it down hard and it resists, then it sends the object up again, only the spring here is the strange behavior of spacetime under extreme conditions. Entropy, the tendency for disorder to increase, creates a puzzle for repeated cycles. Each time the universe expands and contracts, heat and disorder build up, like toys left out until the house is messier than before. If cycles simply repeated with nothing else changing, the universe should get progressively messier, eventually spoiling the possibility of neat, similar cycles. Modern bouncing or cyclic models try to solve this with tricks such as stretching space enormously between cycles so that leftover disorder is diluted, or by invoking processes at the bounce that somehow reset the relevant degrees of freedom. These fixes are clever, though not yet fully confirmed, and they aim to keep each new cycle hospitable to structure formation and the kinds of physics we observe. Observations give clues that steer which cyclic ideas are still viable. The cosmos is currently observed to be expanding at an accelerating pace, which makes running the clock backward into a simple, symmetric contraction harder to arrange. Also, patterns in the cosmic microwave background, the faint afterglow of the early universe, and searches for primordial gravitational waves place limits on the kinds of bounces that could have happened. In practice, that means many early cyclic concepts needed revision, and contemporary proposals now explicitly incorporate the observed acceleration, or rely on forms of physics that act very differently at extremely high densities. Detecting a distinct ripple pattern or a subtle statistical signature in the background light would strengthen some bounce scenarios over standard single-bang accounts. Practical differences between bounce models show up in the kinds of signals scientists look for. Some models predict fewer or different primordial gravitational waves, while others anticipate slight non-randomness in the distribution of early density fluctuations. Searching for those signatures is like inspecting a shaken soda for bubbles that tell you how it was handled. The details are subtle, but measurable in principle. Until such a smoking gun appears, bouncing and cyclic views remain intriguing alternatives that highlight how much we still have to learn about the universe when it reaches extremes. A little cosmic humor fits here. Whether the universe behaves like a well-trained pogo stick or an unruly mattress remains to be seen. Multiverse scenarios, outsourcing the ending. Some scientists think our universe might be one bubble among many, and in that picture the way our cosmos ends could be decided by something happening outside our bubble. In plain terms, the multiverse idea says there might be other regions with different physical rules, and an event in one of those regions could reach or affect us. Picture a neighborhood where each house has its own backyard weather. A storm in the next yard could blow over your fence. This is the basic idea behind outsourcing the ending. the cause of our final curtain call comes from beyond our local patch of reality. It sounds dramatic, and a little like asking your weird next-door neighbor to take out the trash for you forever. One clear mechanism people discuss is bubble collisions that come from an inflating background. Think of a pot of soup where bubbles keep forming, sometimes two bubbles meet, and the place where they slam together gets messy. In cosmic terms, if a nearby bubble with different conditions expands and slams into our bubble, it could rearrange or even destroy the structure of our space. A household example is a crack that starts in one window and spreads across the whole pane. The initial break happens somewhere else, but the whole pane ends up compromised. Short and unsettling. Another route is the idea of vacuum instability, explained without the jargon. Our vacuum might be in a kind of temporary comfort zone that could shift to a more stable but very different state. If such a shift starts somewhere else and reaches us, it would sweep through at essentially the speed of light and change the rules for particles and forces as it passes. A simple way to picture that is a row of dominoes knocked over from one end. The fall begins at a point you didn't touch, yet it decides the fate of the whole line. That sounds final, and yes, you wouldn't see it coming. Quantum branching, the notion that every tiny event might split reality into many outcomes, offers another take. Your universe's end could be one branch among many, while other branches continue with different fates. Consider writing several drafts of an essay at once. One draft gets deleted, but the others still sit on your hard drive. This doesn't rescue us, but it reframes the end as a local decision in a much larger tree of possibilities. A little funny, perhaps, but it's comforting to think at least one branch keeps going to tell the tale. Some theories involve entire higher-dimensional sheets or brains that can bump into each other. When two brains collide, the energy can create violent events that look like beginnings or endings for the universes living on those sheets. If that sounds strange, imagine two plates banging together and sending a big splash into the air. The splash changes whatever was on top of the plates. Physicists search for indirect fingerprints of such encounters, odd patterns or subtle anomalies in the sky, but so far nothing conclusive has shown up. In practical terms, this means outsourcing the end is a headline-grabbing possibility but not a daily concern. No matter which of these pictures you prefer, the takeaway is simple: the cosmos might not be self-contained when it comes to its final fate. Outsourcing can be convenient in business. Not so convenient when applied to the universe. Still, thinking about these scenarios stretches how we understand cause and effect on the largest scales, and it gives the final chapter a cast of outside contributors instead of a solo performer. The role of information and cosmic memory. Information is the way the universe keeps track of what has happened, written into the states of particles, light, and motion. In plain terms, information means the pattern or order of things, like the arrangement of letters in a book or the order of photos in an album. When those patterns change, the record of past events changes too, but the imprint often lingers somewhere. For example, footprints in wet sand tell you someone walked there earlier, even after they left. In the cosmos, faint signals in light or gravity play a similar role, acting as a kind of universal diary. Entropy is a word scientists use to describe how spread out and scrambled information becomes, but the idea is simple: a tidy room has low entropy, a messy one high. When things mix and spread, cream in coffee or perfume in a room, the original order is still implied by the way molecules are arranged, yet it is practically impossible to put every molecule back where it was. That practical loss is important. On the smallest scales, physical laws tend to preserve information in principle, like a perfectly recorded video. In practice, though, the recording gets corrupted beyond recovery. Think of it as a hard drive that eventually fades into static. The bits may technically be present, but you will never read them again. Black holes are extreme examples where questions about information get dramatic and a bit comic, as if the universe misplaced its filing cabinet. A black hole takes in matter and light and hides them behind a boundary. Early on, it looked like anything thrown in simply vanished from view forever, which worried physicists because it seemed to erase information. Later work suggests the universe might be sneakier. the information could be stored at the black hole's edge or leaked back out in a highly scrambled form, much like shredding a document and scattering the pieces across a windy field. Recoverable? Maybe in theory. Practical? Almost certainly not. Quantum behavior adds another wrinkle. Tiny systems can hold delicate correlations that serve as memory, but interaction with the environment quickly washes them out, a process called decoherence. Put simply, those tiny quantum notes are very easy to smear. An everyday analogy is stirring sugar into tea. The sugar's original clumps are gone after a few stirs. That smearing doesn't mean the universe has erased the sugar molecules, it just means the original pattern is no longer recognizable. And when patterns fade, the cosmic memory becomes less useful for reconstructing the past. Cosmic signals that survive over long times act like postcards from earlier eras. Light from distant objects, chemical patterns in stars, and faint ripples in gravity carry records of processes long gone. These are reliable but limited. You might compare them to an old photo album where some pages are smeared or missing, the broad story remains, but small details get lost. Even the clearest postcards become less legible as the universe expands and energy spreads thinly, so future observers would find it harder to read the cosmos history. If the universe keeps spreading and entropy rises, accessible memory will dwindle. Systems that once could store and process information, stars, planets, living things, even clever machines, will break down or become too sparse to function. The endgame for cosmic memory is not necessarily annihilation of data, it is the shift from useful, readable records to diffuse correlations scattered across vast space. Picture a library where every book has been shredded and its pages blown across an endless plain. The words are somewhere, but reconstructing a coherent story is impossible. Still, there are hopeful and quirky ideas about where information might hide. Some proposals say the universe encodes data on surfaces, like a hologram where a two-dimensional pattern holds three-dimensional content, a strange thought, but easier to grasp with the example of a credit card strip that stores lots of data in a slim strip of plastic. Whether the universe actually uses such a trick remains a topic of research, and the bottom line is that physics keeps insisting information cannot be destroyed outright even when it looks like it has been. That stubborn conservation gives a faint comfort. Cosmic memories might be conserved in principle, even as they fade from any practical use. So the role of information and cosmic memory is a tale of two losses, theoretical invisibility and practical unreadability. The universe keeps writing itself into everything, but the ink spreads thin and pages tear. Everyday experiences, spilling milk, shredding documents, or losing photos when a phone crashes, mirror the large-scale story. A little humor helps. The universe may be a bad librarian, but at least it's thorough about keeping scraps of its history, even if it files them in an almost impossible-to-open cabinet. Life in a dying universe, survival strategies. Scientists expect the universe to become colder and more diffuse over time, and that shift forces a rethink of what survival even looks like when energy is the scarce resource. People and organisms here on Earth cope with scarcity by storing food, insulating homes, and finding shelter. The same basic ideas scale up. For example, squirrels bury nuts for winter and bees make honey to get through lean times. Those simple behaviors show the power of small, reliable reserves. In a cosmos where bright, concentrated sources of energy grow rare, conserving and collecting every bit of usable energy becomes the most basic rule. One practical approach is to cluster where energy still concentrates, because localized hot spots matter. Think of living close to a campfire instead of out on a frozen plain. In space terms that means staying near objects that keep putting out heat and light. Long-lived stars or places where matter still falls and releases energy are the cosmic equivalents of a campfire. Another route is to build extremely well-insulated habitats that slow the loss of heat and make tiny energy supplies go farther. A thermos keeps coffee warm the same way good insulation keeps a settlement livable. Small examples on Earth include root cellars and insulated cabins, which show how thermal design stretches limited warmth, and they can teach the same lessons for larger, long-term shelters. Maintaining biology and knowledge requires redundancy and low-power thinking. Seed banks and DNA archives are real-world models. The Svalbard Global Seed Vault stores duplicates of crop varieties so plants survive disasters. Similar redundancy could preserve life's blueprints on a cosmic scale. Digital information should be stored in multiple formats and places, and on media chosen for longevity rather than speed. Paper can outlast some electronics under the right conditions. Likewise, thinking in terms of slow, low-maintenance life cycles helps. Some microbes and tiny animals can persist in stasis for long periods by slowing their metabolism, and learning how to induce and control metabolic slowdown in larger organisms is a useful direction. It's a bit like putting your devices into airplane mode to save battery, except the device is an entire ecosystem. Social organization and simple technologies will be as important as fancy gadgets. Small, tight-knit communities that share skills and resources waste less and adapt faster than sprawling, energy-hungry societies. Closed-loop ecosystems that recycle air, water, and waste are not science fiction. Submarines and some space station modules already reuse many resources for months at a time. Teaching basic repair skills widely, storing manual tools, and keeping local seed and medicine caches are practical steps that work on Earth and would scale to more ambitious habitats. Humor helps. A culture that can laugh while fixing a leaky pipe will likely outlast one that can't. Finally, think in terms of flexibility and diversity rather than a single, perfect solution. Preserve multiple strains of crops, multiple habitats, and multiple ways of making energy because failure in one approach should not doom the rest. Simple measures now: distributing backups, building insulated storerooms, encouraging low-energy lifestyles, are low-cost and high-impact. And yes, pack an extra flashlight. Life's best survival tricks are old friends: store, insulate, share, and keep the knowledge safe. Timescales, from trillion years to forever. Red dwarf stars, much smaller and cooler than our Sun, are the true long haulers of the cosmos and can keep burning for trillions of years, steadily converting hydrogen to helium at a snail's pace. Larger stars flare brightly and die young, like rock stars, but red dwarfs are the slow-burning night lights of the universe, flickering gently while everything around them changes. Picture a tiny camp stove left on low for longer than any human lifetime multiplied many times. That's how these stars behave. Once even the red dwarfs have used up their fuel, the universe moves into a much quieter phase where light is scarce and the structures we know, galaxies, bright stellar neighborhoods, lose their sparkle. At this point, what happens next depends on a few deep questions we still don't fully answer. One possibility involves a process called proton decay, which would allow the building blocks of atoms to slowly fall apart. If that happens, ordinary matter would eventually fade into radiation. Think of it like a melting ice sculpture left in a warm room. Over a long time the shape disappears and only puddles remain. Scientists are still testing whether protons actually decay, so this is a real fork in the road for the universe's long-term story. Black holes become starring characters in the later chapters because they can hang around even after stars are gone, gobbling occasional leftover matter and holding on to mass for eons. Quantum effects cause black holes to lose mass very slowly in a process sometimes called Hawking radiation, which is like a leaky bucket that drips so infrequently the bucket seems immortal. Those leaks will eventually empty them, but only after timescales vastly longer than the trillions of years era of red dwarfs. If protons do decay, the last heavy objects will disappear and what's left will be an extremely thin soup of particles and radiation. If protons are stable, tiny cold remnants like dwarf stars or lone planets could persist effectively forever. The long-term fate often described as heat death comes from the idea that the universe will keep expanding and energy differences will smooth out until there's nothing left to drive change. Entropy, a technical word meaning a measure of disorder or the loss of usable energy, will climb until no more useful work can be done, and the cosmos will be a very cold, dark place where everything is close to uniform. That's like pouring a hot cup of coffee into a big, cold hall and waiting until the temperature is the same everywhere. No stirring of the cup can bring back the heat. Depending on the true nature of dark energy, which pushes the universe's expansion, another extreme called the Big Rip could someday pull structures apart, but current observations make the slow fade into heat death the more straightforward outcome. So when we say, from trillion years to forever, we are describing a chain of epochs, a long stellar twilight dominated by red dwarfs, a deeper darkness shaped by particle stability and black hole physics, and finally a near-eternal state of low-energy sameness unless unknown new physics changes the script. The precise details hinge on experiments and discoveries yet to come, and that uncertainty is oddly comforting. The universe's last act isn't fully written. Meanwhile, humans can safely worry more about ordinary deadlines than cosmic ones. After all, even the longest cosmic clocks run on a scale that makes a missed meeting look impressively punctual. Philosophical and cultural reactions to cosmic doom. Different societies show a wide spectrum of responses when confronted with the idea that the cosmos might end, and those responses reveal a lot about what people value in life. Some turn to stories and rituals that frame an ending as part of a larger narrative, using myths, prayers, or communal gatherings to make sense of something so vast. Others strip the question down to practical choices, asking what should be done now if the future is uncertain. Philosophers and everyday people alike debate whether an eventual end makes life less meaningful, or whether it intensifies meaning by making each moment rarer. Simple examples from daily life surface all the time. Someone writes a list of things they want to do before they die, a church holds a vigil, a comedian posts a joke about buying all the snacks. Practical ethics become central in many conversations. If the future might be cut short, should we prioritize short-term comfort or long-term projects? That debate shows up in boardrooms and kitchens, parents deciding whether to homeschool, activists arguing for emergency policies, or friends planning a retreat instead of investing in a distant retirement fund. A philosophical movement sometimes called long-termism argues that caring for countless future people matters a great deal, which pushes some people to support things like planetary defense and disease prevention. By contrast, other thinkers use older ideas like Stoicism, focus on what you can control and accept the rest. Those approaches offer concrete actions: do the chores you can, call your loved ones, and stop refreshing news feeds when it makes you anxious. Art and popular culture often act as a mirror and a pressure valve at once. Films, novels, songs, and visual installations explore cosmic endings so audiences can practice feeling the feeling without actually being in danger. A gallery might stage an installation that mimics a planet slowly losing light, while a singer writes a melancholy ballad about sunsets and second chances. Humor appears everywhere: dark jokes, memes about "last day on Earth" playlists, or people making elaborate end-of-the-world dinner plans that include foods no one will share. These cultural responses do real work. They help people bond, perform grief, and turn abstract dread into something human-sized. Religious and spiritual traditions adapt as well, sometimes by reviving ancient end-time stories, sometimes by reinterpreting them to emphasize consolation and continuity. Rituals can be practical: community meals, letters of closure, or shared art projects that leave something meaningful for those who remain. Philosophers ask whether belief in an ultimate end changes moral duties to future people or whether our obligations are limited to those present. These debates influence policy and private choices alike. For example, conversations about how much to spend on disaster preparedness versus social programs often reflect deep assumptions about whether the future will exist for long. Social movements respond with a mixture of urgency and creativity. Some groups mobilize to prevent nearer-term threats that could truncate human flourishing, arguing that taking action now is the only responsible response. Others focus on resilience, building communities and local knowledge so people can cope if larger systems fail. Personal examples are small but telling: neighbors forming barter networks, families practicing emergency plans, artists running workshops on how to tell your story in case you can't tell it later. Those are not just practical measures, they are cultural expressions of care in the face of uncertainty. On the level of individual psychology, reactions vary from denial to acceptance, and back again. Some people find that the idea of cosmic doom sharpens priorities and clarifies what matters, prompting reconciliations and simpler lifestyles. Others feel paralyzed, overwhelmed by the scale of the problem and turning to distractions or gallows humor. Either way, the cultural products people create and the conversations they hold provide routes for meaning-making. A neighbor choosing to plant a tree because someone should have planted one can be as profound as a philosopher writing an essay. Both are attempts to respond to a final horizon in ways that keep life humane, funny, and stubbornly hopeful. Future technologies and attempts to change fate. Researchers and engineers are actively building and testing tools to protect Earth and its inhabitants from cosmic and planetary threats, while others outline far-reaching ideas that could change how life survives in the very long run. Practical work right now focuses on stopping rocks and managing our climate, and there are clear examples to point to. The planetary defense test where a spacecraft deliberately bumped an asteroid to change its path showed that nudging a dangerous object is a doable tactic. That kind of test is basically a crash test for the solar system, minus the airbags. One of the clearest approaches is simply changing the path of an incoming rock. Hitting it with a fast-moving spacecraft is the cosmic equivalent of giving a bowling ball a gentle push so it misses the pins. Another option is a gravity tractor, a heavy spacecraft parked near the rock that slowly tugs it off course using gravity. Think of it as a very slow and patient tow truck. In cases where time is short, experts discuss using powerful explosions to vaporize or fragment an object, but that carries risks, like turning one big problem into many smaller problems. All these methods have real-world analogs. We already practice precision towing and controlled demolitions on Earth, and those day-to-day skills help shape plans for space. Altering the amount of sunlight reaching Earth is another active area, framed by both space-based and ground-based ideas. Proposals include putting huge reflective sheets or mirrors at stable points in space to reduce incoming light, which works like putting up a giant parasol for the planet. On Earth, injecting tiny reflective particles into the upper air to bounce sunlight back out is often compared to the cooling effect seen after large volcanic eruptions, nature's own reminder that shading works but has side effects. Geoengineering can buy time for other solutions, but it can also change weather patterns in unpredictable ways, so it raises big questions about who decides and who pays. Looking farther ahead, people imagine much grander engineering, building swarms of collectors around stars to capture their energy, or using dense objects like black holes as long-lived power sources. These ideas sound like science fiction and are technically enormous, but the basic motivation is simple. If you want to keep civilizations running when local resources decline, you need massive, reliable energy and the means to move or rebuild. Think of it as planning from tending a campfire to running a city-sized power plant. The gap between tools we can build today and these grand schemes is huge, yet each small step in space infrastructure and energy management makes the next step a little less fanciful. Preserving life and knowledge is another practical strand that already has examples on Earth. Seed vaults and hardened archives are ways to keep biological and cultural backups safe in case of disaster. The idea is similar to making copies of important files on different hard drives. Closed living systems are being refined aboard orbiting stations and in isolated habitats on Earth, teaching us how to recycle air and water tightly, a necessity for any long-term life support. People also talk about moving entire habitats off-world or underground to escape a ruined surface. Submarine life and remote Antarctic bases offer small-scale lessons in how to thrive in sealed, harsh conditions. A touch of humor helps here. When packing for the apocalypse, you might want to include a good water filter and a playlist, and engineers are working on both in their own way. No single technology can flip the script on the universe's ultimate fate, and many of the boldest ideas remain speculative and resource-intensive. Cooperation, steady testing, and building on simple, proven steps, like diverting rocks, managing climate carefully, and storing seeds and data in multiple places, are the realistic path forward. In short, humanity is learning to be less surprised and more prepared, one sensible experiment and one ambitious plan at a time. Open questions and why the ending matters. We know some things and many things remain unclear. Observations show the universe is expanding and that the expansion is speeding up. That speeding up is attributed to something called dark energy, a name for whatever is pushing space apart. Think of it as a mysterious pressure in the empty parts of the universe that we do not yet understand. Telescopes watch galaxies move away like dots on a blowing balloon, and those motions are clues, but they do not tell us the whole story. There are a handful of plausible outcomes, and each one depends on that unknown behavior. One possibility is heat death, which means energy gets spread so thin that stars burn out and things become cold and dark, like a battery drained to a trickle so your flashlight barely glows. Another is the Big Rip, where the expansion accelerates so much that galaxies, stars, planets and eventually atoms are pulled apart. Imagine stretching a piece of taffy until it snaps. A third is a collapse back to high density, sometimes called a Big Crunch, which would be like a souffle falling in on itself. There are also more exotic ideas, such as the vacuum of space shifting suddenly into a different state and wiping out familiar physics, comparable to a bubble of different soap film popping into the room and replacing everything inside. Which of these scenarios could actually happen depends on how dark energy behaves and on details of fundamental physics that we have not yet measured. Why those open questions matter goes beyond satisfying curiosity. Finding the true cause of cosmic acceleration would reshape our understanding of nature's rules, the same way learning about quantum mechanics once changed technology on Earth. For example, breakthroughs in basic physics have historically led to practical tools. Lasers and semiconductors came from abstract research, so understanding deep cosmology could, in time, yield unexpected applications. A more immediate consequence is how it frames long-term thinking. If the universe heads toward an inevitable, cold fade-out, that changes philosophical conversations about the future and the value we place on preserving knowledge and life. On the other hand, if abrupt changes like vacuum decay are possible, even if extremely unlikely, they force scientists to refine models and clarify what is truly safe. Answering these questions also directs how we build experiments and plan observations. Astronomers map how far and how fast galaxies recede, like watching cars on a distant highway to judge the shape of the road. Particle physicists probe tiny building blocks in labs to see if fundamental forces behave as expected. Improving instruments and combining different kinds of data, light from distant explosions, patterns of galaxy clustering, and precise lab tests, helps narrow down possibilities. Patience is required, since the cosmos does not reveal its secrets quickly, but each new measurement trims away models that don't fit. Finally, there is a human side to this uncertainty. Knowing whether the universe has an end, and what kind, influences culture and imagination, fuels art, and motivates generations of scientists. The questions are big enough to be humbling yet practical enough to push technology and collaboration forward. And while these cosmic endings may feel remote, the search for answers teaches us how to ask better questions here on Earth, about our planet, our future, and how to make sense of being tiny actors on a very large stage. A little cosmic mystery keeps science lively, and a touch of humor helps us endure the suspense. After all, figuring out the universe's finale is a lot harder than predicting the next plot twist in a soap opera. So, quick recap, scientists imagine a few main ways the universe could end. One is the slow fade, everything drifts apart and cools like a campfire that finally burns out. Another is the tear, if expansion keeps speeding up, it could pull stuff apart like stretching a piece of taffy until it snaps. There's the collapse idea, the whole thing falling back in on itself like a bounced ball coming down. And there's the wild card, a sudden change in the fabric of reality, kind of like a popped soap bubble that rewrites the rules. We also mentioned tiny leaks from black holes over time so long they make your calendar look like a child's doodle. None of this is happening tomorrow, or in a million human lifetimes, so you can keep using your coffee mug without panic. Think of these scenarios like different endings to a very long, very slow movie. Some are quiet, some dramatic, most are way beyond our daily worry list. If you liked exploring these big ideas with simple examples and a little humor, stick around. Tell me in the comments which ending surprised you most, or what cosmic question keeps you up at night. Hit like if this made the cosmos feel a bit less scary, subscribe so you don't miss future videos, and click the bell if you want a reminder. Next time we'll dive into black holes up close, the mystery of dark energy, and whether life could ever adapt to a changing cosmos, all explained simply and with a few laughs. Thanks for watching, and see you in the next one.